So yesterday we talked a little bit about mass spec and the useful peaks that you can analyze in mass spec. The most important peak, arguably, is going to be your parent ion. That's the peak that's tallest in the rightmost cluster, right? So if you look to the far right of your mass spec, you'll see a cluster of peaks in that area. It's going to be the tallest one in that region. And that tells you the molecular weight, which is a really important thing to know, right? If you've got an unknown compound, you want to know how heavy it is. And then we continued on and we said you can actually look at the mass plus one peak as well. And the mass plus one peak, the intensity of it compared to your parent ion tells you roughly how many carbons you have in your compound. That's really useful for helping you identify the molecular formula. And then we went through and did an example where we tried to deduce the molecular formula of an unknown compound. The next thing we're going to do is we're going to switch to the mass plus 2 peak. You're probably wondering, why is there a mass plus 2 peak? Mass plus 2 peak is a really useful hint. It indicates that you have a bromine or a chlorine. So if we look at chlorine, chlorine's a little bit unusual. Chlorine 35 is the major isotope. This is abundant around 75% of the time. And then chlorine 37 is present around 24% of the time. There really is almost no chlorine 36 present naturally. So you don't see a mass plus 1 peak for chlorine, but you do see a mass plus 2 peak. With bromine, it's even stranger. There's bromine 79 and then bromine 81. Bromine 79 is present about 50% of the time. And bromine 81 is present 49% of the time. So if you see that mass plus 2 peak, that's a big indication that you've got some sort of halogen on there, specifically bromine or chlorine. And the other cool tool with this is you can identify which one you have, whether or not it's a bromine or a chlorine. If you've got a chlorine, you're going to be looking at something that's roughly a 3-to-1 ratio. So if your parent peak is roughly 3 times as big as that mass plus 2 peak, you likely have a chlorine. If you've got bromine, the mass plus 2 peak is about the same size as your parent ion. And this is a 1-to-1 ratio approximately. So let's go ahead and look at a really simple example. This is for chlorobenzene and bromobenzene. So if we look at these spectra, we can identify our mass peak, or our parent ion. That's the tallest peak in our rightmost cluster. And then over here, we've got this mass plus 2 peak. And then in between them, you can see this little itty bitty mass plus 1 peak, and you can use that still to determine the number of carbons in your compound. And you can see this is roughly a 3-to-1 ratio, which is a big hint that you've got that chlorine on there. If you go over and you look at bromobenzene, all of a sudden these peaks are roughly the same height. And so you can say, hey, this is a big clue that we've got a bromine on there. And this is always going to be in a 1-to-1 ratio. If you don't see a mass plus 2 peak, that's a good indication that you don't have any bromines or chlorines too, so you can rule those out as well. So that's a really simple, easy tool you can look at. Does that make sense? If you go into weird inorganic compounds, you'll run into all sorts of odd isotopes, but as organic chemists, we're primarily concerned with that upper right-hand corner of the periodic table, and we're not even going to address those weird isotope patterns. All right, so let's change gears a little bit and talk about the fragmentation patterns. And the other day, we mentioned that anytime you've got a bunch of carbon groups, it's really easy to see loss of certain carbon fragments. So I typically make a list of clues. The first one is if you've got A mass minus 15 peak, meaning you see a peak that corresponds to your parent subtracted, or take out 15 from your parent. That means it's loss of what? Yeah, loss of a methyl radical. We saw that on our pod. If you don't see that peak, that means you don't have a methyl group on your molecule, or at least most likely it's not a very probable. The next one is mass minus 29. What do you think that is?
Ethyl.
Yeah, loss of ethyl. And then we can go down the chain and we can say mass minus 43 is loss of propyl. And then mass minus 57 and so on would be loss of longer carbon chains. This would be loss of butyl. And then there are some odd ones that you can identify too. Oftentimes you see mass minus 18. Does anybody have an idea what mass minus 18 might correspond to? Loss of water. So oftentimes you see loss of water. And we'll discuss this. Typically this is a good indication that you've got some sort of alcohol present in your molecule. And we'll go over the mechanism for why this occurs. And then oftentimes, if you notice, most of the carbon groups, when they're lost, they're all odd numbers. If you see a big fragment at an even number, that's a clue too. So I'll make a little asterisk here. If you see loss of an even number fragment, that means that you have something occurring called a McLafferty rearrangement. And a McLafferty rearrangement is a big clue that you've got a ketone or an aldehyde. So these mass fragments can be really useful tools for identifying what's breaking apart and how it's breaking. So let's go back a little bit and, yep.
For the even number, is there like a range that should be, or it could be any even number?
We'll talk about that shortly. I want to show you the mechanism first. But anytime you see loss of an even number, it's kind of unusual because normally carbon fragments, when they fall off, are going to be odd number. Yeah. Okay, so we said the other day that some fragments show up a lot more intensely than others too, right? What impacts that? The stability of the carbocations. Okay, so let's make some notes. Some fragments are more likely than others, meaning that they show up at a much, much greater intensity. And this is due to two reasons. The first is hyperconjugation. So for example, if you've got a tert-butyl carbocation, that's going to show up a lot more intensely than a secondary carbocation, and that's going to show up a lot more intensely than a primary carbocation, and that's going to show up more intensely than a methyl carbocation. So hyperconjugation, you can roughly determine which one's more likely based on how intense it is. The next one is resonance. And we already covered this. We said that allylic carbocations are really common and they show up intense or at intense peaks due to the resonance stabilization. And then the last one I said is benzylic fragments are pretty common as well, because these benzylic fragments again have a ton of different resonance structures where you can delocalize that carbocation around the ring. There are a lot of other resonance stabilized fragments that you will see as well, but I want to show you guys some of them using the mechanisms. So a lot of this is review from first term chemistry, right? let's take a look at some common fragments. Okay. So the first one I wanted to do is with alcohols. And we said with alcohols, you often see what fragment or what loss?
Water.
Yeah, loss of water. So let's try to figure out what the heck's going on here. So let's say we've got this alcohol. And I'm going to draw this all out. We've got two lone pairs. Lone pairs kind of stick out like a sore thumb. And if you've got electrons being thrown at your molecule, the lone pair electrons are going to be the first ones to be dislodged, right? So if we take this and we fire an electron beam at it, we're going to remove one of those lone pair electrons. Now all of a sudden, this oxygen's electron deficient. So we've got a positive charge. This would be our parent ion, right? So I'm just going to bracket this. And I'm going to put a positive charge over here because we've lost that electron that used to be a lone pair electron. Now what I like to do is to label my carbons. The carbon with that oxygen coming off is alpha. And the carbon one away is going to be our beta carbon. And then what do you think the next furthest carbon away is? Gamma. So we like to label these as alpha, beta, and gamma carbons based on their positioning relative to the functional group. And this radical is pretty dang unstable. What ends up happening is that this radical will hop down to this bond. It'll steal an electron from this alpha beta position, and then the other alpha beta position, or the other electron from that alpha beta bond will be dumped over onto the beta carbon. So now we've got this fragment plus our beta position now has a radical on it, right? Why do you think this fragmentation is so common? We haven't lost water.
That's a full octet.
Resonance, right? When in doubt. Which fragment's resonance stabilized? Is it the radical? No. We can't see radicals with mass spec. However, if we look at this one, this does have a resonance structure where we can move those electrons up. And now this carbon's sharing that partial positive charge. This fragment's pretty common because it is resonance stabilized. So with alcohols, you commonly see this sort of fragmentation pathway, and you commonly see that loss of water too. You'll see both of them typically. Yep.
Can you explain the preference between the two beta positions and why the one was chosen instead of the other?
So if we would have gone to the other beta carbon, we would have formed a methyl radical, which is a little less likely than an ethyl radical, but it can happen in either direction.
Okay.
Typically, you want to try to favor formation of your most stable carbocation and radical while you're fragmenting, though. That's a good question. Okay, so you can use these clues. You can also look at amines. Amines do a similar reaction.
But water didn't exactly fall off.
No, I'm saying this is another fragmentation pathway you'll see in addition to loss of water. We'll look at loss of water next. Actually, let's just do that now. Sorry, I'm going out of order. Okay, so let's say we've got loss of a water that we're trying to find too. Let's discuss how that happens. And I'm just going to start with our parent ion. And I'm going to label these carbons again. I've got my alpha, got my beta, and then over here I've got my gamma. And in particular, we've got these gamma protons. So I'm going to just draw them in as blue protons coming off. And we know that this is our parent molecular ion. It's got that positive charge. We've already knocked off one of those lone pair electrons. For loss of water, something kind of bizarre happens. This radical is going to abstract a hydrogen from the gamma position. And then the other electron from that hydrogen is going to get dumped over to that gamma carbon. And then this whole group's going to get kicked off in the process. So when this happens, you now have that loss of water. And then let's label our alpha, beta, and gamma. Actually, I'm going to color code this just so we keep track of all our hydrogens. And now that alpha position, because it lost that water, it's going to have a positive charge. And then the gamma position is actually going to be a radical now. And you can oftentimes see this fragment because that water is really, really easy to kick off through this fragmentation pathway. Does that make sense? It's a kind of complicated fragmentation procedure because it involves both double-headed arrows and single-headed arrows. But the key is that it's really, really easy to dislodge alcohols. And anytime you see loss of 18, that means that you most likely have an alcohol present.
It requires a gamma hydrogen.
Yeah, you have to have a gamma position as well. So for example, if you had isopropanol, you might not see this because isopropanol wouldn't have any gamma protons. Okay, so now let's go on to amines. Amines are pretty similar to alcohols where you can kick off one of the lone pair electrons. So for example, let's draw our parent ion where this amines lost one of those lone pairs. It only has one left now. Again, we've got these alpha and beta positions. And just like with alcohols, this can clamp down, steal an electron from that alpha-beta bond, and then that beta position will get the remaining electron. And just like with our previous example with alcohols, this is a really nice cation because it's resonance stabilized. You can move that pi bond up to the nitrogen. Oh. And put the positive charge on the carbon. So this again is resonance stabilized. Does that make sense? So amines and alcohols, you commonly see these fragmentation patterns. The last one we're going to cover is that McLafferty rearrangement, where you oftentimes lose that even molecular weight fragment. And let's discuss how that occurs. And again, this is for aldehydes and ketones. Okay, so let's just take a generic ketone here. And I'm just going to draw a R group coming off one end. And just like before, I like to identify my alpha, beta, and gamma positions. So we've got alpha, beta. Oops, sorry. Alpha is actually one away. So we've got our alpha, beta, and gamma carbons coming off that ketone. And if we look at this, we've got lone pairs. So if we hit this with an electron beam, we're going to kick off one of those electrons. That will give this oxygen a formal positive charge. And the other thing that's really, really important to remember with the McLafferty rearrangement is that sigma bonds can flop around, right? So what I like to do is I like to get that gamma carbon as close as possible to the oxygen. And I'll show you guys why. So we'll go alpha, beta, and gamma. And that's because this gamma position has some protons coming off, and that proton is pretty close to making a six-membered ring. Sterically, that's going to be the most accessible proton to do an abstraction from, right? So if we do this, we know that these radicals can do a hydrogen abstraction. So it's going to abstract a proton from that gamma position. The other electron from the gamma position is going to get dumped down into the beta gamma position. And then last but not least, we're going to break this alpha beta bond. And the alpha position is going to get a radical. I'll be honest, this is a pretty complicated mechanism, and I won't test you on it, but you may see it on some homework problems or on some sapling problems, so I wanted to show you the overall mechanism. So let's go through and try to figure out all of our fragments that came out of this. You see how between the beta and gamma position we formed a new bond? That means that it's an alkene, right? And then over here, our ketone now has a proton coming off of it. And why is this such a favorable fragmentation pathway? Resonance, right? So if we look at this carbocation fragment, you can move the electrons up to the oxygen. You can say, well, this fragmentation is very probable because if you do this, you get a resonance stabilized carbocation.
But wouldn't it be a radical because of the electron on the alpha?
Oh, shoot, I'm skipping steps. There is a radical here. So let's do the full arrow pushing. Thank you. You totally caught me there. All right, so for this one, you're going to pull a pi bond down, or pi bond electron down, and form a new alkene to that alpha site. And then this oxygen's still going to be a radical. Does that make sense? So I'm just going to put the positive charge on the outside. But this is a resonance stabilized fragment. However, it's resonance stabilized due to that radical.
I have a question.
Yep.
When we're drawing those out, is it okay if we only draw out one of the protons? Because we're only concerned about.
Yeah, for the gamma position, you're asking, do you only have to draw one? Yeah. I oftentimes only draw one, otherwise it gets really cluttered.
And why is the alpha position 1 away?
That's fine.
So that's a good question. If you're looking at this as a functional group, this entire group is treated as the functional group. So the closest attached carbon is that alpha carbon. It really depends on how you define your functional group. So let's go back up and look at our alcohol, or our amine for this case. This is our amine. The attached carbon is that alpha carbon. If we go down and we look at our ketone, the attached carbon is at that alpha position.
But isn't the oxygen the functional group?
No, the entire CO double bond with the CH3 or whatever coming off is.
That's what I meant, not including the R group is what I meant. Like, the carbonyl is the functional group, not this with the R coming off, right?
I know it can be confusing, but with any carbonyl groups, the carbon that's one away from the carbonyl carbon is the alpha position. It's just historically how it's always been
That's right.
named.
So why is the R group circled?
Oh, I've just circled it arbitrarily. Sorry.
Okay, now I'm good.
I wasn't sure what you were getting at. So if we look at this, there's a bunch of clues you can get out. The first is this fragment is always an even molecular weight, right? And so that's that clue with the McLafferty. You always get the loss of the even molecular weight fragment. The other thing that's kind of cool is depending on the identity of this R group, you can determine the identity of your ketone or aldehyde. So let's make some notes. If R equals CH3, That means that your fragment will weigh 58. So that's for a ketone. If you have an aldehyde where that R is a hydrogen coming off, it will typically be 44. And then you can also determine, if you don't have a methyl ketone, if you have something like an ethyl ketone, your fragment will typically be 72. So for example, if you were trying to determine, hey, do I have this guy versus this guy, what fragments would you expect for the one on the left?
So 58.
Yeah, exactly. If we were comparing these two, we would say this one, I would expect to have a mass to charge fragment at 58, corresponding to that methyl ketone. However, the one on the right wouldn't have that peak. That wouldn't be a very prominent fragment. What peak would we expect for the one on the right?
72.
Yeah, 72. So this one, for example, you could look at it and you'd say, hey, I would expect a nice big peak. Even though these are constitutional isomers, we can start deducing some of their structural properties based on their fragmentation patterns. It takes a bit of experience to be able to get really good at this, but we're going to practice it a bit more. Does that make sense? There are a few other fragmentation patterns. It's really easy to lose halogens too. Halogen carbon bonds tend to be pretty weak, and so you can pop off a halogen. You might see that in some of your sapling problems, and I think there might be one or two that are covered in your book. They're just not as common. So halogens are the other big one. All right, so let's get down to the guidelines for how we can interpret all of our data. First thing I always do is determine the molecular weight. How can I determine the molecular weight from mass spec? Yeah, the parent ion. So first thing I do when I get a mass spec is look for that parent ion. Occasionally, it's kind of weird, you can't see that parent ion, at least not very well, because your molecule is so unstable it falls apart very quickly. So sometimes you can see it, other times you can't. Do your best to try to identify it, and I'll give you a clue if it's simply not present. The second thing I do is I determine the number of carbons. And what peak helps me determine the number of carbons?
Mass plus 1.
Yeah, the mass plus 1, and we can use that formula I showed you guys to determine the number of carbons. And then third, determine if bromine or chlorine is present. How do I do that?
Mass plus 2.
Yeah, mass plus 2. I like to be systematic with this. And then the other thing I can do is determine if nitrogen is present. How do I do that?
It's an odd number.
Yeah, odd number. If you've got an odd parent ion peak, that means you have an odd number of hydrogens. That's another really good clue. Then the next thing I try to do is try to deduce the molecular formula. And it's important to fill in gaps with oxygen or hydrogen. Kind of like we did the other day, figure out the mass that you're missing and try to fill in that gap with oxygen or hydrogen the best you can. You might not be able to definitively do it, but you might be able to narrow it down to a couple of potential options and then work from there. Then the next thing I typically do is I determine my hydrogen deficiency index. And the HDI tells you a bit more information once you have the molecular formula. What does that do?
Number of rings or
Yeah.
pi bonds.
Number of rings or pi bonds. I should say number of rings plus pi bonds, because you can have combos of both, right? And then last but not least, I take a look at my fragments. And try to match with your appropriate isomer. So for example, on your pod that I gave you, you guys were able to come up with a bunch of constitutional isomers that fit your data. Then what you can do is look at your fragmentation patterns and determine, hey, this fragment makes a lot of sense for this particular isomer that I came up with. So sometimes it's a pretty lengthy problem-solving procedure. Other times it's immediately clear. So like the pod I gave you, because there were so few isomers, you guys were able to do it fairly quickly. When you get into really large, complicated molecules, it's not as easy, and typically you have to have other spectral data to help you out. Does that make sense? All right, so what we're going to do with our remaining time is just do some practice problems. And I pulled these from our textbook. And I'll give you guys a minute to work on these. So talk about it with your neighbor, and then we'll discuss it as a group.
Do you recommend us drawing the molecule, or do you think that's cheating?
No, I think it's an excellent idea to draw the molecule. So that's our molecule of interest, right? And it's saying you don't observe the parent peak. Instead, you observe a peak at mass minus 57. What do you think's occurring? What is mass minus 57, first of all? It's loss of butyl. Why are we losing a butyl group so easily? Okay, so are you guys trying to tell me that we are losing this butyl fragment? That is not what you're saying. Do you care to clarify, Marcus? The tert butyl group, right? So there's a bunch of butyls. The tert butyl fragment, we know if this pops off, it's a nice stable carbocation. So like I said, sometimes your parent ion isn't even detected because you can form a really stable carbocation. So in this case, what we're likely observing is this radical cation combo. So why do you think the mass minus 15 peak isn't present in a very high abundance? So it says, can you explain why the mass minus 15 peak is not the base peak? Remember, the base peak's the biggest peak.
It's not very likely to have enough of it pop off.
Yeah, exactly. We always try to cleave the weakest possible link, right? The weakest possible link in this case is this bond in between that tert butyl group and that butyl group. That one's really easy to cleave apart. It's not very easy relatively to cleave off a methyl group, so you just don't see that as a base peak. Does that make sense? All right, let's go to the next practice problem.
Is that because a methyl wouldn't be stable on its own?
Yeah, it's a lot less stable than a tert butyl radical. Methyl radicals are typically or methyl cations are very small in IR, or mass spec. Holy cow.
That looks like
Consider the following sequence of reactions. Let's try to identify all of the different intermediates. Whoa, it's got a mind of its own. Then check your work with your neighbor too. I'm just going to draw letters out, and then we'll draw in the structures. Give me a thumbs up if you think you got all the different intermediates and products. I'll give you guys more time then. You guys aren't like this?
No. No, I'm writing them as well.
Oh, don't have to draw C.
Is that methyl iodine?
Yep.
Not me.
It's not Mel.
Not me.
That never happened.
My favorite was one time I had a student raise his hand and goes, "What's a cation?" Like, what?
Oh no.
You mean a cation?
Was he from
Oh,
Texas?
yeah.
What's that air cash?
This
How
is
we go to
base.
soda?
So it's going to tackle these substitutes.
Yeah, I don't remember that.
I'm just not sure any it's going to turn this to a number.
And then give me the thumbs up if you think you got the intermediates and product. So I've got a rough gauge. All right.
Well, NaOH is going to deplete the oxygen, right? Oh, it's going to create a...
And for the sake of argument, too, let's draw the major products. So, for example, with part A, we've got beta protons here and here. But let's assume we're going to get our Hoffman product, right? And then work with your Hoffman. Or Zaitsev product. This Zaitsev. Yeah. All right, so compound A we know is going to be an E2 elimination. So we've got an alkene, right? Why aren't we doing substitution? The backside's way too hindered for SN2, right? Anytime you've got a tertiary group with a leaving group, you're not going to do SN2. Okay, and then if we treat A with hydroboration oxidation conditions, we're going to get molecule B. It's going to have an alcohol on it, right? Is it Markovnikov or anti-Markovnikov? Anti. Okay. So it's going to be a racemic mixture here. We're going to get both dashes and wedges for that alcohol. I'm just going to draw it as a straight line. And then for C, we're tosylating it. So now our alcohol is a good leaving group. And then in the next one, we're treating it with potassium terbutoxide. Are we doing substitution? Elimination?
Big bulky base.
And it's going to be Hoffman, right? Okay, so we've made our alkene. And then we're on D, we're going to E. We're going to treat this with MCPBA. What will that do?
Double bond turns into no bond.
Yeah, double bond will turn into an epoxide. Okay, and then with F, we are treating it with methyl magnesium bromide and water. So let's think about this. We've got methyl magnesium bromide over here. Is this going to attack the less substituted side, or is it going to attack the more substituted side? Less substituted side. It's a really strong nucleophile, which means it's going to attack the less substituted side. That means your alcohol will be coming off the internal carbon. And then for the last one, we're treating it with sodium hydride that will deprotonate the alcohol. And then we're treating it with methyl iodide after we deprotonate the alcohol. So what sort of functional group are we making?
Ether.
An ether, right? That's our Williamson ether synthesis. So in this case, it's going to be a racemic mixture because we have created a stereocenter right there, but I'm just drawing that as a straight line. All right, so now let's look at the questions. How can we use IR to distinguish between F and G?
Look for a hairy beard for the alcohol. Or no beard.
Do alcohols have hairy beards or broad tongues? Broad tongues. So you should see a broad tongue in around that 3000 region to be able to distinguish between F and G. Then it says, how can we distinguish between D and E? What do you guys think?
You see some of those SP, you have it.
The CH.
SP2 CS bond.
Yeah, exactly. You remember drawing that line at 3000? If you look at peaks to the left of it, those are indicative of sp2 CHs. We would see that with D, but not E. So you can use that as a clue. You can also see CC double bonds. However, they show up pretty weakly, and they're around 1600. So you can do that as well. All right, and then C is, how can you distinguish between compound B and F? Would you want to use IR or mass spec? Mass spec, absolutely. So we could use mass spec, and we could use that to determine the molecular weight change, right? One of them has a very different molecular weight than the other. So you could very easily do that with mass spec, not so easy with IR. And then with D, it says, would mass spectrometry be helpful for distinguishing between A and D?
No.
What do you guys think? Ah.
I'm saying no.
So we're looking at A and D here. I'm going to circle them.
For things that just have vanilla carbons,
Mm-hmm.
or would you call it molecular weight? Oh no, sorry. What I mean is, if you took off a carbon of A, you would have a positive charge up against a pi bond.
Exactly.
That you have.
Yeah, so Grace was saying on molecule A, if you remove a methyl group, you'd have a positive charge on a pi bond, right? Those aren't very happy. However, if we look at D, what happens if I pluck off this methyl group? We've got a resonance stabilized cation. That means that we'd have a really, really strong fragment correlating to loss of 15 on D, but not on A. So you can actually use the fragmentation patterns to help determine which of the two isomers you would have. All right, I think we're going to stop here for mass spec. If you guys want, we'll take a 5-minute break, and then we'll come back and work on the exam.